is biased towards blade volume and size, a unique and technically challenging project like the Bahrain World Trade Center attracts little interest from manufacturers. But the team finds a solution by investigating a pre-existing blade design.
Lars, could you try to move it a little bit up and down to see if it works? Oh, that's great.
With slight modifications, they determine an older model will survive the wind conditions in Bahrain. They also need to enhance the blade's safety features. Unlike other models, the blades in Bahrain will be spinning on an office building above a shopping mall. But the engineers still need to solve the most fundamental design problem: how to put a turbine on a bridge. They use their scale model to study the bridge's performance in various wind conditions. Like the turbines, the bridge must survive exposure to the high winds between the towers. The structure also needs to be strong enough to bear the 11-ton weight of the turbine. But the turbine will not simply be a dead load. The blades will turn up to 38 times per minute, creating a huge moving force on the bridge. For this reason, the engineers discover that the marriage of the turbine to the bridge could create a disaster scenario, a phenomenon known as resonance. The wind will rotate the blades, but it will also cause the bridge to vibrate up and down. If the vibrations of bridge and turbine are ever the same, they will begin to amplify each other, increasing and intensifying until finally the bridge can no longer bear the force. To avoid this catastrophe, the engineers decide to make the bridge design more rigid. This will actually make the bridge vibrate faster than the turbine, eliminating the risk of resonance. But wind tunnel tests reveal another potentially deadly hazard. If the wind changes direction or gusts suddenly, the blades of the turbine could deflect and strike the bridge. A normal wind turbine on a vertical axis is tilted back 5 degrees to avoid the possibility of the blade striking the pole. But that's not an option on the bridge. Each blade is capable of deflecting more than a meter back. To avoid blade strike, the sides of the bridge's front edge are drawn back, creating a slight V shape. The modification creates a distance of 1.7 meters between bridge and blades, enough to avoid a disastrous strike. In theory, the new bridge and turbine design works, but the move to the real world involves many unknowns. With turbine and bridge design complete, the dream of the world's first wind-powered skyscraper is closer to being realized. But there's still a long way to go. On the construction site in Bahrain, senior section manager Simon Hill must keep the project on schedule. The elliptical shape of the towers hasn't made his job easy.
The problem we've got here in terms of the concrete, it's not a square shutter system, it's all curves. So all your shuttering systems are all curved, you're climbing the building up on curves, you've got to set out on curves. It's very difficult to do that. You have to get it right first time. If you start to go wrong, you've got a terrible job to get it back in place.
Although the building presents unique challenges, Hill believes it's all worthwhile.
This is a unique structure. You know, there are a lot of buildings around the world about the same height, but there's nothing to compare to this. There's no other building in the world that's got the features that this has got.
2.5 years after breaking ground, the Bahrain World Trade Center finally reaches its apex of 240 meters. Now the construction crew must tackle their most dangerous task yet, the raising of the bridges. Each weighs 68 tons, and lifting one is an act of absolute precision. The bridges are shaped aerodynamically like aeroplane wings. Hanging on cables, their sleek shape makes them very difficult to control in high winds. The crane operators lift them slowly, gaining only 11 meters per hour.
Slow the power pack down. Go to the slower speed. Just a little bit more on the east side, Jack. West side, stop.
Workers only bolt one side of each bridge to the towers. The other end is placed on solid steel rollers. As the wind catches the sail-like shape of these towers, it will make them sway. This, coupled with their expansion and contraction in Bahrain's sun, means the towers will slowly move back and forth. These rollers will allow the towers to move freely, up to ½ meter every 10 seconds. But as it goes on, the gap between bridge and tower leaves no room for error. Clearance is just 30 centimeters on one side, 60 centimeters on the other. If bridge and tower collide, the damage could cost hundreds of thousands of dollars.
Jack, we need to come up about 50 mil on the west, so the strokes clear the direction back. Yeah, okay.
The third bridge goes on at a dizzying height of 133 meters. Everything is ready for the next phase. The raising of the generators and blades.
So we're going to split into two teams. One team's going to go with Dave to do the turbine, and the other team's going to stay down here to set up the propellers.
We have one plane in that direction, one plane going down there.
Ola Sangil and Lars Thorbeck fly in from Denmark with their teams. On a construction site of this scale, any delay in schedule means a serious loss of money. So the engineers have been given 7 days to complete the task. There's no time to lose.
Can you get hold of Joseph for me? We may need him to do a bit of translation.
I'm going to get the lads at toolbox talking in a minute.
An advanced crew already installed 2 of the generators. But the top one still needs to be lifted. At 50 kilometers per hour, the wind is too strong to lift anything. But the crew gets it ready in case the wind drops. They raise the 6.5-ton generator slightly off the ground and let it find its balance. The wind still gusts from the southeast. But lift supervisor Dave Root thinks there might be a buffer zone in the shadow of the east tower.
Level 3, straight away, Babu. Level 3. Right now. 35 now. Okay, right on. Gonna go. Okay.
The wind levels off to 35 kilometers per hour. Dave Root decides to go for it. His plan works. The generator goes up quickly, ascending 133 meters in minutes. 18 bolts, 27 millimeters thick, will lock it in place. But first, Dave Root has to reach them. He's harnessed in, but it's still a long way down. He tightens the last one. Despite the high winds, the crew has managed to stay on schedule today. But the sternest challenge remains. All 3 sets of blades must now be assembled, raised and bolted to the generators. Keeler's brilliant idea may unwittingly present the team with their toughest test. Raising aerodynamic blades between 2 towers designed to accelerate wind will be an unprecedented challenge for everyone involved. The following day starts out with a stark reminder of the wind's unpredictability.
We had a storm last night, so I think it just gusted up. The wind speed got up to 110, which we've never heard before, and it blew from the south. Currently we're at 85 wind speed. There's no way we're going to be lifting anything. Forecast is not good.
The engineers have set 21 kilometers per hour as a cut-off point for lifting the blades. Anything higher is unacceptable. With winds howling at 85 kilometers per hour, all they can do is wait. Sean Keeler designed this building to funnel and accelerate wind. At their base, the breadth from one side of the towers to the other is 126 meters. But the wind hitting the building is being squeezed through a gap only 33 meters wide. While all this wind will be good for the turbines once they're mounted, the crew must first deal with the problem of lifting them in such an environment. In addition to wind speed, the engineers also need to consider the wind's direction when they raise the blades.
Because if you have a lot of wind on one side and no wind on the other side, it will be more difficult to control the rotor.
The diameter of the assembled blades measures 29.2 meters. This is just 3.8 meters less than the span between the buildings. A collision would mean a huge loss of money and time. The team assembles the first set of blades and connects them to the central hub. They want to be ready just in case the wind drops to 21 kilometers per hour. Each blade contains 50 layers of fiberglass glued together around balsa wood reinforcements. At 13.4 meters, each one is strong and highly flexible. But each is also aerodynamic, shaped to catch the wind. This will make them very difficult to control as they ascend.
So in principle, we use the ropes to control the movement of the rotor in this direction and in this direction, and also that it doesn't start to tilt.
What you're saying is you want a rope on that blade, a rope on that blade. Okay,
Yes,
do no harm, do no harm.
Yeah.
Long ropes will help the ground crew keep the blades from colliding with the building. At 3 p.m., the wind drops. They need 2 hours to complete the lift. If they don't go now, they'll run out of daylight.
We're down to 21. They're up on the bridge now. Norman are up there. They're giving the all clear. So we're taking the load up. It's starting to go up now. So we're ready to go.
One lift hauls a set of 3 blades bolted to the hub, weighing a total of 4.2 tons. At this position, the main tower crane is stretched to its maximum lift capacity.